can You did it the same second that I said it. Awesome. Okay, so before we get into our talks, we've been showing people's introductory slides. I only noticed one person who hasn't shared their slide yet that's here. Let me just share real quick. It's one of our speakers. So Neeraj, would you like to introduce yourself?
Yes, of course. Hi, good morning and good afternoon, everyone. I'm Neeraj Gupta. I work at IUCAA in India, and I have been working on extragalactic surveys of 21 centimeter line primarily for last several years, but have also been interested in OH at the same time to get a better handle on the physical state of the gas. But of course, it has been somewhat this line is much weaker than 21 centimeter and harder to detect. So I'm very happy that we have all gotten together to discuss this and overcome this challenge in coming years.
Ellen, thank you so much. Okay. Ooh. Just give me a sec. Working with limited screens here. I have no idea what's going on. Okay. All right. So we might just dive into the talks. The schedule has Michael up first. Is Michael here? Oh yeah, Michael's here.
Yeah.
Are you ready to go, Michael?
Sure.
Over to you then.
All right. Let me share my screen. Can you see my screen? Oh,
Yeah. Oh, I see a screen.
you see that?
Yep, now I can see it. Yep.
Okay. All right. Yeah, so thank you very much for this opportunity. Yeah, I saw that the title of the session is OH absorption observation. So I tried to orient myself on that title. And I don't know, touching on some other topics on the way. And I would like to acknowledge my collaborators from a recent paper and from the Tor and Tor GC collaboration in general. So yeah, I guess we already had a lot of introductions to this topic, but the interesting thing about the interstellar medium is really that it's that there are so many different scales. So there are so many different processes on so many different scales at work, and there are also so many different phases which interact and change into each other, and so it's very all of these scales dominate the cycle of matter in our galaxy, of molecular clouds forming out of the diffuse ISM, in which then stars form, which at the end of their lifetime give matter back into the diffuse ISM. And with DOH lines, and so my talk is mainly focusing on DOH lines at 18 centimeter. We can really probe different stages in this matter cycle, both with absorption or emission, so quasi-thermal OH excitation, but also with maser emission, which I guess the later half of the conference will be more focused on. So I guess this has been shown before, but just as a reminder, so I'm going to be focusing on the OH lines, which arise from the hyperfine splitting of the ground state of OH, and there are four transitions. The two strongest ones are often called the main lines at 1667 and 1665 megahertz, and there are two weaker ones, satellite lines. And OH absorption really has been has been the first molecule detected in the radio, and you see here this first OH absorption observations towards CAS-A. As I mentioned, OH can also be amazing when the levels are pumped, and here the the excited rotational levels come into play, which in itself also show hyperfine splitting and give rise to OH transitions at higher gigahertz frequencies. But then there are also the infrared transitions, which are the pumping lines, which themselves can be used in absorption to trace OH. So yeah, there's a very, very complex picture and very, very versatile picture which the OH lines let open to us. Basically, they open to us a very versatile view of the interstellar medium. And just on the topic of the session, here probably not complete overview of OH surveys. So there have been surveys since the basically beginning of radio telescopes and the OH detection. So by Miller-Glass in 1968, but then also Turner in 1979, which really mapped a lot of the famous continuum sources and looked for OH absorption and also OH emission. More recently, and here I only target OH absorption surveys. There's the SPLASH survey, which is a single dish survey, but also sees a lot of OH absorption. This is in the southern hemisphere. The ongoing gas cap OH survey with the ASCAP telescope, which is going to map OH at very high sensitivity and resolution, again in the southern hemisphere. We did the survey of OH in the northern hemisphere, which I will talk about mainly in this talk. But then there have also been all sky surveys here, mainly targeting background quasars in different surveys with Arecibo, the VLA, and the ATCA. Which really probe very deep with absorption towards very strong continuum sources. And I guess we will probably hear more about this in other talks in this conference. And I just wanted to mention there, like, since we had a talk about optical absorption yesterday, there are OH lines also detected in the interstellar medium, at least, of OH in the optical, but also in the far infrared, as I mentioned. So transitions into the ground, rotational transitions into the ground state, which could be observed with SOFIA until recently, and has also been used, and there are papers out from that. So here I will focus on the TOR survey, which basically covers a large part of the first quadrant, where we map the OH 18 centimeter lines, both the main lines and the satellite lines. And basically the most prominent thing are OH mesas, as you all probably know. So they come in different flavors, which I don't want to go into here a lot, since we will cover this later in the conference. What we were looking for was OH absorption. So we looked at the strongest all continuum sources which we detected and looked for absorption in the main lines, but then also characterized all OH transitions. And this was a sensitivity limited sample based on the continuum strength, which we recently increased by doing a set of 3 very deep OH observations with the VLA, where we targeted one Jansky bright sources and looked for OH absorption also at very high spectral resolution. And here just an example of this. So basically these are the four lines as I showed before, and so here we really detect very narrow, weak OH absorption features, which is probably expected, but just to give an idea. The result of the study was that we confirmed a very tight relation between OH and OH column density and molecular gas column density here traced by CO. So H is readily observed molecular gas. We confirmed previous evaluations of the OH abundances, both with respect to molecular and total column density of hydrogen, and we found this remarkable correlation across really different types of molecular gas associated with different types of environments. So both in high-mass-darkening regions, which are these black dots, and but also in diffuse lines of sight. And the reason why this is interesting though is really this lower part, because there have been there's this long-standing question which I think we probably already covered in the talks yesterday in parts of the CO dark gas, which has been found both with gamma ray and dust observations across the sky, also in C+ emission, and there is a postulation that OH should be present in this H1 to H2 transition region and could be a good CO dark gas tracer. And there have been observations which indicate that this is indeed the case. So this is both in emission here, for example, this study by Michael Bush, seeing this very broad OH absorption emission feature towards the outer galaxy, but also these very high sensitivity observations with Arecibo towards strong centimeter background continuum sources, which detect quite a big number of CO dark gas features. The study I just presented, we only really probe in this upper part of, so I'm taking the study because it shows directly OH absorption. So we only probe in this upper part where people where previous studies expected CO dark gas, and we only find one detection, which and basically, however, we do see that for the sample we probe here, especially the ones with the weaker OH absorption features, have significant contributions of atomic gas, and so they've significantly lower atomic molecular gas fraction than 1. We also looked for other indications for CO dark gas. So we looked for C+ emission with Sophia. We only had this towards 2 lines of sight and only detected one clear C+ emission feature corresponding to an OH feature. This was generally turned out to be a quite difficult experiment if you don't do this statistically. But yeah. The other thing we checked was if there are abundance gradients with galactocentric radius, since that has been expected, at least if you go out in galactocentric radius from the C+ emission, that the fraction of dark molecular gas should increase. In our data, given the scatter, we couldn't detect it, but we also couldn't rule it out. With that, so far our study, what's really exciting is that many of the next generation telescopes will allow us to really probe galaxy-wide into the regime of CO dark gas. So here, this is just an example of some estimates which we did for potential observations with the DSA 2000, and we think we can really probe here for sources down to 100 millijansky, in continuum sources down to 100 millijansky in strength, significant parts of the CO dark regime, which in the end will allow to do really galactic tomography of the CO dark gas. Yeah, this is so far for future studies. A thing which we are working on right now is to look at OH in the galactic bar region. This is a follow-up of the TOR survey, which we extended beyond the galactic center. And here we are mainly interested in H1, the dynamics, star formation, and the geometry of spiral arms and dust lanes, and the magnetic field. But we're also looking at OH at very high spectral resolution. Here's just an example of mazes towards Sagittarius A star. These are AGB stars, mainly in the galactic bulge. Things which have been looked at before, but we will provide a continuous survey of the entire bar region, which is potentially interesting. With that, I'm at my conclusions. So there are really a numerous amount of surveys which target OH absorption across the galaxy, and the future is bright. Future telescopes will allow even deeper surveys, which hopefully will probe in really in a homogeneous way into the CO dark regime. I showed some results from the TOR survey where we find and confirm tight correlations between OH and other molecular gas tracers, and we're able to measure the abundance with that. And with the TOR GC survey, we really hope to study OH in the galactic bar region and draw conclusions on the structure and dynamics of molecular gas. Thanks.
Thank you so much for that, Michael. Do we have any questions? See some thumbs up. Oh, you've got a question?
Maybe later. Neeraj first. Yes. Thanks, Michael, for a great talk. Then, can you get back to the slide where you show the CO dark gas as a function of galactic to centric? Yes, distances. So you see that very clearly the increase in trend of the fraction of molecular gas in here. So in this case, the CO dark gas, how did you calculate that? Do you use the same axial for this for calculation?
So this on the right is PNID et al. 2013. This is the result from the CO from the C plus from the C plus emission. This is our result on the left. So we were looking if we see this trend, covering this. We're covering this part basically, and so the only thing I'm saying here is that we didn't find a significant trend over this part of our observations. We couldn't rule it out either. The scatter is significant. But I was just curious if we by any chance did see it.
Oh yes, thanks for that. I thought you used the same axial factor, but no, yeah. Okay, thanks, Michael.
Neeraj?
Hi, thanks, Michael. Very interesting talk. I had the same question exactly on the same figure which Heap asked. I wanted to understand if there is a way to understand, let's say this abundance ratio is not changing with galactic centric radius for OH. Is there a way to understand that?
Yeah, I mean, so again, so we really can't rule it out. So we don't have a statistic. We don't find a correlation here, but it's also that the scatter is really significant. So, and we only probe a small range so far. So we really need to add in get more data at higher galactic centric radius. Yeah, I don't know. We can
Okay.
speculate.
Yeah, this kind of
uh,
thing is always I find it very interesting that how we can sort of get something out of this to understand something in extragalactic
yeah,
where we have even more little, much little information. Yeah.
definitely. Also, I mean, from like yes, one could probably maybe argue that the scatter goes down here. One takes away this point, but okay, then we're yeah.
One
We
little
need
question.
a higher sample size, I think.
Yeah.
That help. Even though that's normally not the answer, but yeah.
Yeah. Do you also have some information about dust content or visual extinction across towards these sightlines?
So not really, because I mean these are we really probe. So this is an extragalactic continuum source. So we really probe the entire line of sight through the galaxy, and yeah, like this is no at this part we don't really have
Okay.
we didn't look at the dust extinction. Something to look at, especially for the local the local OH. That would be super interesting.
Okay. Yeah. Thanks.
Malcolm, you had a question?
Yeah. Do we know what the total mass is of CO dark molecular hydrogen?
Yeah, so it's so there are different estimates. So I think the GOTC plus survey had something around 30% of the molecular gas that's CO dark. There's some studies which put it a bit higher.
Right. Yeah. Thanks.
Is it still the case that that there's a bit of a sensitivity limit on that? Because I've seen follow-up papers where they re-examine a region with higher sensitivity and they're able to recover a lot of that CO.
That may well be. I mean, I think these observations here from for year 2018 and I mean I'm probably gonna hear more about this in the next talk, but in the next session. But I mean these observations are really, as far as please correct me, but I think here these are really deep CO observations with ERAM. So I from my impression from the literature, these CO detections or non-detections were robust. Upper limits. As for the GOTC plus survey, that may well be that they're like once you take normal standard CO surveys that you get you can follow up and get detect some CO where you don't see it initially when you use galactic plane CO surveys. Yes, I'm sure there are cases. I mean, we also saw this in this study. So these ones we had dedicated apex observations, and we did find, like, integrating very deeply. We did detect CO also in this very faint OH feature. So in the end, we only had one feature, which was CO dark. Features which we would probably not have picked out in the standard CO surveys.
Do we have any more questions for Michael?
Yeah.
Sorry, it's me again. Can you go back again to the slide? Yes, this one.
Yeah.
Yeah, I'm very interested in this increasing trend of the fraction of molecular gas as a function of the distances from the galactic center. Do you have any interpretation for that? I'm just thinking about it really.
Why the CO dark in general?
Yeah.
Okay. So I,
What I usually think is that we have the inflow. Yeah, well, methodology. Yes, I think so. Thanks, Michael Bush. I think it's like the inflow from the preceding gas from the CCN into the Milky Way, for example, and then and then there's a lot of star formation quite close to the center, and then gradually, when the stars ages, they would migrate into a larger radius. So I'm not sure if there's something similar to this.
Yeah, I mean, as Michael just put in the comment, I mean like metallicity is a strong factor which goes down if once we go out towards the outer galaxy. I guess there's also less dense gas. Yeah, it's the two things which come to mind.
Yeah, if I can add on this, because I'm also interested in this plot. So Mike, are you saying that you think the OH abundance should change with galactic radius?
Well, yeah, that's a good point. So I was just looking in our data if you see
If you found one.
if we see any,
Okay.
I think obviously I think we cannot really rule it out either because this
Yeah, because I think it's pretty.
but it's I think like
Yeah.
as soon as we go, like I think starting here, I think where this data stops. I think we should if OH is tracing. So in our data, I did this test mainly also because one worry we had was that since we're comparing it, we use CO as CO dark as molecular gas tracer, right? So we should it's okay. I guess there are two different questions for our data. One was if the CO dark gas fraction is increasing, then the CO, since it's in the denominator, so the H2 from CO is in the denominator, that should drive up the abundance.
Right. Oh yeah, I see what you're saying.
And so I was expecting it here. And then the other question was, does the abundance itself of OH change?
Yeah.
Yeah. So that I'm not sure if the abundance itself changes. I was
Because
yeah.
I interpreted the plot on the right as to say that CO itself just becomes faint.
Yeah.
So you're not tracing molecular gas of CO.
Yeah.
Whereas the denominator in that plot is C+.
Yeah.
So
yeah, so in the left, sorry, I didn't explain this fully. So the denominator here is in the NCO, so therefore
yeah.
I was so we were testing two things, I guess. Yeah.
Yeah, because I'm not. Yeah, I don't know if the abundance should it should change because the metallicity is changing, but I'm not sure by like how. Yeah, it's an open question, right? Because like, what is the OH column density sensitivity limit, or like the lowest column density you have in this survey?
I think it's 3 times 10 to the 13.
Okay, yeah, and this 10 to the yeah. Which I think from the data from Sophia, I think this abundance ratio is pretty constant down to like 10 to the 12. But then after that, we really just don't know.
Yeah, no, you're right. I mean, so this plot here was mainly also to probe how like how bad our NH2 measure was. And if you see any so yeah, it's more you're totally right. It's more probe of that than of the OH column density. Yeah. Of the OH of lack of any changes in the OH abundance or
Gotcha. Yeah. Cool.
Yeah, thanks.
Thank you.
Neeraj, you had your hand up?
Michael, I have a quick question. In this abundance ratio in the left panel, uh, no, the previous slide itself, the one which we were, in this one, the denominator H1 and H2 are based on emission. Like, is that correct?
So H2 is derived from CO.
Okay.
H1 is derived from H1 absorption.
H1 is derived from H1 absorption. Okay. Okay, I was wondering if the sizes of clouds can be different for OH and H1 absorption, because that is something which we see in extragalactic measurements sometimes.
This is true. Like
And that can lead to some of the scatter here, which we need to address in future.
excellent point. Yes, excellent point. So we had only, so for some data we had only standard CO surveys available, which had 46 arcseconds. And I mean this source is an extragalactic source, so it's tiny. We did do follow-ups with Apex of the 2-to-1 lines. So these come out at 30 arcseconds, which is a bit better, but it's still not. It could still be that we see that may affect our ratios. That's a good point. Yeah, I don't know, maybe some ACA observations or so.
Okay.
Get it down a bit better, a bit more. It's a good point. Thank you.
Do we have any more questions for Michael? Ending you?
Hi, Michael. Also, it's exciting to see your results. I have two questions. Can you change to the previous slide? Yes, this one. So you did not find any gradients towards the galactic radials. But
so not significant, right? I mean, the scatter is quite high.
Yes. I checked your paper. So you used a constant excitation temperature of 5 kelvins to calculate the OH current density. Yeah, right.
Yes, that's correct.
And another assumption is that you use 13 CO to estimate the H2 column density.
Well, we use actually no, like, okay, for the black, we ran into problems with 13 CO. We did some tests and found that we were significantly underestimating the H2 column density. So we for the diffuse, so for the very weak OH features where 13 CO was very weak or not detected, we used the 12 CO emission. These are all the blue dots, and the black dots are indeed 13 CO.
Okay, will these two assumptions affect leads to this result?
Yeah, this is a good point. I mean, the excitation temperature, we don't have we don't have we don't have a clear way in this case for this data to derive the OH excitation temperature. But one could maybe in the future think about something like Anita has done from Amoeba, using some of the single dish observations in the surroundings. Although this is really in the galactic plane, so even the single dish observations are an absorption. I don't know, one should look into this, but so there was no straightforward way to estimate the excitation temperature. So yeah, I mean this could affect the data in principle. So another reason why I wanted to look at this plot in this way was that black dots show OH, which is is associated with molecular gas in giant molecular clouds which have star formation in them. So these are likely more dense than the blue dots, which are line of sight OH absorption features, and both of them show similar. And we also discussed this. Both of them show similar abundances, and also don't show very different behavior in this galactocentric radius plot. So in that sense, so that gave us a bit of confidence that even though we take very simple assumptions for the OH excitation and the CO excitation, we were hoping that it doesn't affect our results too much.
Okay, thank you. So my concern is that the OH abundance. So you showed in the y-axis. It should be the OH ratio compared to the CO ratio, CO current density, OH current density compared to the CO current density. So if the OH is coexist with CO, so you will have this nature result. Right.
Yeah, I mean, so yeah, we used the standard conversion factor for the H2. That is correct. So yeah,
so it's not OH abundance.
I mean, it's a proxy for it.
Yes. So maybe it is possible to use other parameters of H2 molecular hydrogen. So
sure, yeah, no, definitely. I mean, so this is so since we had only 3 lines of sight, right? We really want to get the spectral dimension, so therefore we didn't go for dust as an H2 tracer. So this was the one we had, the possibility we had at hand. But I agree. I mean, this is a very simple assumption, and I'd be happy to improve this with future observations. Definitely. Fair point.
okay, thank you. So we in our previous studies we find a relation between the OH current density and the OH excitation. Maybe we can use that relationship to calibrate the excitation temperature of OH, and that can be used to in your study.
That would be super interesting. Definitely.
Okay, thank you.
Yeah, we should talk offline.
Yeah, sure. Thank you.
John, I saw your hand go up earlier. Did you have a question?
Well, thanks. I just sort of wanted to ask a kind of wacky question, but since everybody's interested in this same topic, you know, the Einstein A factor for CO is so big that it's awfully hard to keep it excited so that you can see it in emission. You know, you need densities of 500 or, you know, at least several hundred. So my question is, and this is to the whole group, not just you, Michael, but excellent talk. What if there were two different phases of molecular gas? You know, in the Milky Way, we think, and in many other spirals, we know that the radial dependence of several things goes together with the same exponential scale length. And that's the ionizing radiation field, it's the hot young stars, it's the CO giant molecular clouds, and it may be other things like cosmic rays. And they have a fairly short scale length of, you know, maybe 3 to possibly 3 or 4 kiloparsecs in the Milky Way. But the H1 and presumably the cool neutral medium as well as the warm neutral medium have much longer scale lengths. But suppose there is also a molecular phase with a long scale length that is very, very hard to see because CO certainly would never show because the density is low. But we can occasionally see with very high sensitivity OH absorption. And Michael Bush's talk yesterday got me thinking about this. Is there anything that would rule that out? That is, that there are 2 different scale lengths. See, that then you would expect exactly the figure that we see on the right hand side of the screen there, that the ratio of one to the other would be rising, which is essentially just the ratio of the two exponential scale lengths. Is that crazy, or is that possible?
Michael got his hand up before
I
me.
see, Joe.
Go on.
Okay, yeah, I feel like we have both strong opinions. This has been kind of like a pet theory of mine for a few years. I've never written it down anywhere, but you know, from Bush 2021, which Michael showed earlier, it's like I think Ron, Allen, and I had kind of shown that there was kind of like a constant molecular surface mass density going out with the H1. And my kind of theory about that is that just towards the outer galaxy, which just happens to be where we are in the sun, you know, past the 8 kiloparsecs, the mean volume density of the general ISM is quite low, like less than 500 particles per cubic centimeter. And we'd always played around with just the very simple theories of, you know, looking at the critical densities. And even though you can get some optical depth effects to help out the critical density for CO, when it's, you know, when there's very little CO, I assume it's probably closer to like, you know, 800 or closer to the optical thin limit. So whereas the critical density for OH is still 1 particle per cubic centimeter. So, you know, that's in the optical thin limit too. So I think that could be part of what's going on, in addition to you know, the metallicity effects and the chemistry, that you also have the lower volume densities in the outer galaxy. And when you look for the OH, apparently the OH is there in heaps, probably because it's generally excited and like collisionally excited in these lower volume density environments. And that's kind of what we showed in Bush 2019 too, is that the mean volume densities for the CO dark gas is much lower by 200 or 300 particles per cubic centimeter on average than the CO bright features towards the outer galaxy. So I don't think that's crazy, but maybe Joe has another idea.
No. I was just going to say, how do you define phase? Because I think if you want to define phase by, is it seen in CO or is it not seen in CO arbitrarily, basically according to density, I would have said, then I think we already know that it does show the behavior you just described. Like, I'm not sure whether it also has a higher scale height, but it's certainly, as shown by the plot on the right and as shown by Michael's work, and as expected by theory, the place where you find the CO dark molecules is when it's a bit diffuser and it's a bit warmer, and so it's either the envelopes of existing GMCs or whatever, or it's in more diffuse regions. So, which would manifest like the plot that we're seeing on the right, which is also, I think, is it kind of equivalent to saying that what you just said, John? Is it just a semantics issue about what the meaning of phase is?
But I don't know if the volume density has much to do with the C+ emission.
No, I mean,
it's more of a
C+ has
chemistry
shown up in
thing.
all kinds of different phases, right? C+
Yeah.
shows up throughout, and then you subtract what you think you know from the other ones. Isn't that
But if
right?
we're just, yeah.
I'm just like, if I get John's question right, he was saying, do we have evidence that there are 2 phases in the molecular gas? And I was just going to ask you to precisely define phase so I could understand how that, what we already know, which is sort of what Michael just said.
Well, could we define these 2 phases differently in terms of their scale lengths, radial scale lengths in the Milky Way? Because there we know already that there are 2 phases. You know, the things that I described a moment ago. So, I mean, I wish we could do CO absorption the way we do OH absorption, because then we sort of might be able to tell how much CO is just locked up in the ground state. But I agree with you, Michael. It's very hard to excite the CO in low density. So
we've done CO absorption. Dan Rybarczyk's doing work with CO absorption compared against HCO plus absorption, which also traces the diffuse, you know, second phase, if you like, of the molecular ISM. And he's pretty much, he's shown pretty conclusively that the CO just isn't there. That you've got CO absorption where it's dense, and then where it isn't dense, apparently really well mixed with the CNM, you have some molecules.
I have some slides on that later, but it's probably not ready for the session. But yeah, but those are very nearby sight lines, or you know, those latitudes where we have the quasar absorption for the HCO plus have to be kind of highish latitude, so like above a 5 or something. So they don't get a lot of velocity as in the Bush 2021 sight line. I do say in Bush 2021 that it's a thick disk, so the scale height I imply is about 200 parsecs, and I don't show any latitude spectra because I didn't like the funky baselines, but I still implied that they were, and the referee was cool with it. So, yeah, I have those sightlines, but we do see the OH more extended in latitude than the CO, if that was part of your question also, John.
Yeah, thanks, Mike. This is super interesting. But John, with this second phase, this on large scales, is that also in latitude? Is that also more extended in latitude, or?
Well, it will certainly flare. The disk flares in the H1 as you go outside the solar circle. But that's partly because the surface density of stars is reduced, so the gravitational potential becomes flatter. But yeah, I mean, I think there's at least a factor of, well, 1.5 to 2 in the scale height, even inside the solar circle, between the C and M, the cool neutral medium, and I don't know if Trey's still online, he might argue about this, but between the atomic cool medium and the CO. So there is a vertical scale height difference as well.
I just remembered a paper we wrote with Philip Engelke, which also compared a quiescent random piece of sky which was Bush 2019, and the W5 star forming region that showed very conclusively that volume density played a role in why we didn't find any CO dark gas in W5. So maybe I'll link that if people are interested. But if I'm understanding correctly, the phases that John has just described would, I think, primarily just be based on CO brightness, but due to density or other things, metallicity maybe.
And also there are results directly measuring H2 absorption spectra in UV that I believe show that the CO dark H2 sightlines are warmer as well, at least warmer in terms of the molecular hydrogen excitation. I can find a reference for that somewhere. And some of the excitation modeling implies it's warmer as well, although I'd want to revisit the assumptions made in those models.
Joe, can you talk a little bit about warmer? How much, like in Kelvin?
I'm sorry, can you repeat that?
You said like the CO dark gas will be warmer or could be warmer. So
yeah, so
how
there's
much,
one thing,
like
there's one paper I've used in a bunch of talks, and now and I should double check exactly what it was, but the temperatures were quite similar to the CNM temperatures. It was sort of like median or mean of like 90 Kelvin-ish. I mean, it was not quite as warm as the CNM, but it was getting there. I'll dig out the paper and I'll put it in the Slack. And hopefully I haven't misquoted it, which is always my fear. Like it's someone else's work that I pulled into a slide once and may not have examined all that closely, but
So this is H2 absorption in the
yes.
Okay.
In the UV, I think.
In the UV, yeah, okay. Is that then also extended in velocity?
Don't remember. It'll probably be off-plane sightlines against IB stars.
Because this is still remarkable about your results, Michael, that it's so extended in velocity, I think. I mean, because I see the different phases, but this is just some smooth layer with, I don't know. I mean,
I just interpret it as being basically wherever you've got the atoms, then you've got the molecules too. Or two, with Michael, your work, Michael Bush, sorry, not Michael Rugel. With Michael Bush's work, the spectra displayed were a big average, right? They were stacked. So there's going to be some smoothing that comes out of the stacking, I assume. But in Dan Rybacek's work, and Bush is involved in this too with me, we should have a paper coming out pretty soon, I think, actually, that is looking at HCO+, which behaves very much the same way as the OH in terms of tracing the dark stuff. And with that, it really looks like it's mixed with CNM, or mixed, at least there is the sort of good component match as far as we can tell.
I can post a plot in the Slack. I don't know if
Yeah,
John would
you just did that.
Yeah. But if people are interested, I just posted in the session 7 Slack where this is towards 3C111, which goes right through the California molecular cloud. green is OH emission of the GBT, red is HCO plus absorption, and then blue is CO absorption, where it's very sensitive. I don't know how sensitive, but Dan assures me that if there was CO, it would show up, and you just don't see it outside of the California molecular cloud.
And we've got some molecular fractions as well towards those, the CO dark sidelines, and I can't remember what they are either. Dan was revising the paper again, wasn't he? There was something he finished off.
It'd be interesting to see what like CNM fraction is, because I know John has found like a pretty constant CNM fraction with gas cap. Do I have that right? Gas cap H1?
Yeah.
Out towards very large radii?
Yeah, well, we only had one big gas cap field, but I have
Okay.
seen that actually even in the Southern Galactic Plane Survey and the VLA Galactic Plane Survey, that you do keep on seeing the absorption lines where you could see them, that is towards continuum sources and where there isn't a big warp. The warp in the first quadrant makes it a little hard. But in the fourth quadrant, you can see a long ways across the disk at low latitudes.
Yeah, I kind of think that this plot on the right just keeps going up, and we don't know how much CO dark H2 is out there. Like, probably is 100% CO dark fraction out to the boondocks, but I just can't tell yet.
Thanks so much, Michael, for that talk and all the discussion that it sparked. This is so good to see. But we might go to our next talk, which is Neeraj going to talk to us about MALS. Yeah, you ready to go?
I'm going to share my screen, and please tell me when it's visible. Is it visible now?
Yeah, looks like it.
Okay. So I'm going to focus more on extragalactic side of things, and will try to summarize what we have been doing over last maybe 10 years or so. And you will notice that the progress is not as rapid as what we have seen in the galactic ISM, but I hope I will convey the optimism that that we are moving in the right direction, and hopefully we can accelerate from here on with the new telescopes coming in, and all of us also sort of discussing and collaborating further. So on this my title slide, I'm showing an H1 or OH absorption that we detected a few years ago. This was using a Westerbork telescope, and the kind of system this is shown here in the left panel. So background is an optical image, so we can see a galaxy, and there is a filament towards the right hand side which is extending, and then there is a bright radio source. It's the quasar Q0248 plus 430, and quasar is at a redshift of 1, and this galaxy is much more nearby at redshift of 0.05 approximately. And then it produces 21 centimeter line absorption, as we see in the right panel, the topmost one in that. And then there is a 1667 megahertz weak absorption detected as well, but 1665 megahertz is of course much fainter, and that is not detected. So this is the kind of investigation we would like to extend to nearby galaxies and even higher redshifts using bright radio sources. And the idea being that then using this in combination with 21 centimeter line, we can get a handle on how is the cold neutral medium and the diffuse molecular gas is evolving as a function of redshift. And then we can relate it to the bigger question of how galaxies are acquiring neutral gas and then converting into the molecular gas and stars. So this is the intermediate phase that we are trying to look at through H1 21 centimeter and OH 18 centimeter absorption. And then so that can sort of allow us to find this additional piece in this puzzle to understand why do we see such a rapid evolution in the evolution of star formation rate in the universe. So what we need to do for this is to have lots of bright radio sources for which we can take spectra very efficiently, and that has been a big challenge over last many years. So this table is like basically showing about 10 such sightlines, as I showed here in the previous slide, which we were able to observe. Again, it took us like 5 to 6 years to just get all the data because we had to use 3 different telescopes, VLA, GMRT, and WSRT. And that was because as we remember, just the previous generation of telescope didn't have very wideband instantaneous wide bandwidth, so we could observe only one line at a time. And then, of course, sensitivity was also very limited. So each target was observed for approximately 10 hours to get some kind of a sensitivity which is reasonable to detect OH. To overcome some of these limitations, what we did was that we selected sight lines with this kind of configuration, which already showed 21 centimeter absorption. So when we pick up sight lines like this, where a background radio source is close to an optical or H1 disk, it's not necessary that we always see absorption. The sight line may be passing through, but gas is patchy, and it's only 10-20% of the cases we see absorption. So this gives us a handle on what is the cross section of the gas that is producing absorptions. So when the observing time is so limited and precious, it's pragmatic to look at sight lines first, which are showing only 21 centimeter absorption. And also from the physics point of view, we can argue that like if there is a sight line which is not showing H1 21 centimeter absorption at all, likely it will not have any OH also. So it's not a completely sort of a biased kind of a study, practical but also physically motivated at the same time. So when we observed these 10 sight lines, we actually detected OH absorption only in one case. And that was this case which I showed here in the previous slide. And this is the diagram which Serge also showed yesterday. So when we had this 1 out of 10 detection, which is shown here in this plot as blue stars, and you can see most of them are upper limits, and there is one filled symbol here which is showing representing the detection. We wanted to make some kind of an understanding, and the only context that we could get to was like, okay, what has been seen in our galaxy, and even those measurements at that time, like which is like 2018 when we wrote this paper, were sparse. Of course, now there are many more sightlines, and we should update this one. But this is what we found at that time, and so we look at these measurements extragalactic in blue, and we can see that like we have tried to reach to the sensitivity which is like 10 to 13 to 14 per centimeter square. So we are just getting into the diffuse ISM here, and the galactic measurements which are shown in red, there are lots of upper limits, very sensitive measurements here going down to 10 to 12 to 13 per centimeter square, but there are most of the detections are in the regime where we are also detecting or detected at least one case, but rest of them are upper limits. So of course, like next one big step would be to improve the sensitivity on these measurements. But we also have 3 extragalactic measurements here in black triangles at the top, and these are have the column densities of 10 to 15 per centimeter square or even more. So these 3 are corresponding to gravitational lenses. They are at somewhat higher redshifts between 0.2 to 0.9, and they have been known for actually about 20 years total, like detected at different times from searches through gravitational lenses. That's how these sightlines were observed. But knowing these 3 for a long time now, we have one more, so that is 4. So this has been the status of extragalactic OH absorption line studies when we are talking about gas detected from intervening galaxies, that we have very few handful of systems. The top panel here shows the detection rates based on OH column density. So we can see that like the detection rate increases as we go towards the lower column density. So sensitivity definitely helps in this case. But when we look at its dependence on H1 column density itself, which is the x-axis, we did not really find any particular dependence in this case. And of course, the scatter is also very large right now. But this is one of the reasons I was very intrigued by the plot which Michael showed related to abundance ratio, and that it also generated a lot of discussion. So we have to see with better data whether it holds like this, or we do see some dependence here with H1 column density as well. So this is one of the next steps that we would like to investigate with the future survey. So this is the big picture that I was talking about, that if we can put both H1 and OH together, we can actually get a understanding of physical processes that are deriving these evolution of star formation rate density. And with Meerkat absorption line survey MALS, we are targeting this redshift range 0 to 1.5, and to be able to observe two transitions which are so close in frequencies, that is H1 and OH in this case, is very, very important, especially when we are talking about atomic phase and the molecular phase at the same time, because sizes of these clouds can be different, and this is something which we are all finding from some of the VLBI measurements as well. So that will be an additional thing. So just to introduce what MALS is, so it's a large survey project which is happening at Meerkat Radio Telescope. Over last 4 years, we have been acquiring data, and we are observing approximately 400 pointings at L band and UHF band. So total frequency range covered is 1670 megahertz to 580 megahertz. So this means that we do cover OH main lines up to redshift of 1.5. 1.8 rather, and for H1 21 centimeter we cover up to redshift 1.45. So it's like a very ideal kind of a setup to be able to search for both these lines simultaneously. And we have optimized the sensitivity of our survey such that we can detect 21 centimeter absorption up to few times 10 to 19 per centimeter square for 100 Kelvin gas. And for OH, simultaneously, this implies that we are able to trace like 10 to 14 per centimeter square or higher. So really not as deep as we would like to, but still it's much better than what has been done so far. So this is our survey footprint, just showing to give you some visual picture of like how these different pointings are distributed, because this is a southern telescope. So you can see that most of the stuff is like in the southern hemisphere. So that's the idea. And this is one particular sight line I wanted to show. This is a gravitational lens system. In the plot which I was showing here, this is where this system is PKS 1830 minus 211. So this has been known for sometimes a 10 Jansky radio source at redshift of 2.5, and it has got a very interesting absorber at 0.89, which corresponds to the lensing galaxy. And these are the OH lines which have been known previously from this. And when we observed with Meerkat kind of sensitivity, we were of course able to get very high dynamic range spectra for H1 21 centimeter and OH, but we were also able to detect OH satellite lines, which we didn't even plan for. And this is just 45 minutes of integration on this sight line compared to the 10-hour integration that I was showing, and the very faint absorption that we detected. So this is just to demonstrate that, like for each pointing or each radio source that we have in our survey, we can actually get very high quality spectrum that can cover both H1 and OH lines, and has very good sensitivity compared to what has been possible before. So this is now showing OH, different OH lines for this particular absorber here, PKS 1830 minus 211. This is redshift 0.89. So top two panels are 1667 and 1665. So these two lines are exactly in LTE. So if you look at their ratio, they just turn out to be 9:5, very well. But when we look at satellite lines which were detected for the first time, we find that only 60% of the column that we see in absorption can be explained by what we see here in the main line. So there's definitely some non-thermal excitation which we can see here additional. And in 1712 megahertz, we do see that a part of this actually appears in emission and another part which appears in absorption. And I believe this is something which we will discuss more in next couple of days, that this is this interesting behavior of satellite lines demonstrated by OH in particular situation of infrared pumping, that one satellite line can appear in emission and other can appear in absorption. This has provides interesting constraints on the physical conditions in which these lines are arising, but also these kind of transitions if they are perfectly inverse to each other, can be very useful to constrain fundamental concepts of physics also. That's another reason that why looking for OH and in particular these kind of transitions is very attractive for extragalactic astronomy. And this small blip that we see here, significant in this case, it will correspond to luminosity of 6100 solar luminosity. So it's highly luminous system here in this case. And this is to illustrate the kind of issues that can arise when we are looking at gas in different phases, like molecular or atomic, especially when the molecular is corresponding to high frequency lines, the CO. So what we are seeing here in these two left panels is how the background radio source is a lens system. will look at very high frequency. This is in ALMA at about 100 gigahertz. But when we come to centimeter wavelengths, we can see that there is much more diffuse emission that is corresponding to the radio jet, which is visible now at lower frequencies corresponds to. So what we are seeing here is that although the foreground galaxy is the same, of course, molecular gas and atomic gas have different structures as well, but the background radio source that is illuminating the foreground gas has actually different distribution, different illumination. And as a result of it, we can see that H121 centimeter line is much more uniform. But when we look at HCO plus, H2O, CH plus, and other dense gas tracers, they are actually showing much more clumpy distribution. So if we have like this kind of high quality data, we can actually try to constrain what could be the scale height of gas which is giving rise to H1 and OH absorption, and also what could be the origin of these different clumps that we are seeing in absorption. So this is the kind of thing that is possible, and these are the differences that we may have to take into account when we try to interpret extragalactic data. And this is why another reason I think that combining H1 and OH instead of combining, say, H1 and OH with CO could be little more practical and interesting, especially if you can understand the relationship between OH and H2, as Michael was showing, and yesterday Serge was also implying. And so that could actually turn out to be a combination which is less affected by systematics, and also practically it turns out to be observations and data which is easier to acquire, because the same kind of wideband setup can provide both H1 and OH lines in this case. So we have to make progress with to build a context to understand what we will see from MALS in extragalactic case. We have started looking at also the galactic component of MALS, because every sightline that we see with MALS or the Meerkat telescope is actually also passing through our own galaxy. So if some H1 or OH gas is present, it will produce that absorption as well. And of course, ours is an extragalactic survey, so we are looking at high galactic latitudes only. But that is not a totally negative thing for us when we try to interpret our extragalactic data, because it's primarily the diffuse ISM that we are looking at. And of course, like, we will try to bridge gap with what we see in the dense ISM in the galactic plane, but that we hope that that's the kind of information that can come from galactic surveys which are primarily targeting galactic disks, and through this then we can try to build the complete picture. This is just like some of the examples of 21 centimeter absorption that we have detected from our surveys, and all these data have been made public. Currently, we are looking at OH frequencies, and in next few months, our hope is that we can get some first order understanding of it and make that also publicly available to everyone to use. And this is my summary slide to just give the overall context from left to right. So I started with showing that, okay, in last 15-20 years, we have added one more sightline of OH, but maybe we now have slightly better understanding of like what the kind of sensitivities that we should target to do better OH extragalactic surveys, which is what we are applying to Meerkat absorption line survey. And yesterday's Serge talked about that how in diffuse ISM we can, in a much more simpler way, relate OH to H2 abundance. And knowing H2 abundance can then help to put it in the larger framework of understanding how the physical properties of ISM are. And then since H2 in absorption is also detected at redshift greater than 2 in optical spectra of quasars, we know what is the cross section of this molecular gas at higher redshift in that case, right? But again, since it is observed in optical and UV, again, we are limited to diffuse ISM. But the question that we can ask when we compare, say, OH measurements that come out from our galaxy or from, let's say, radio survey like a Meerkat absorption line survey, is that the cross section that is predicted by these H2 measurements at redshift greater than 2, does it compare well, or is it different with respect to these measurements coming from radio? Because that would then answer potentially two questions for us. One is that it can tell us that how the H2 cross section itself is evolving. That of course will be an obvious thing, and also we can indirectly try to answer if there have been a lot of dense gas that has been missed in these large optical ultraviolet surveys at redshift greater than 2, because that would, if that is the conclusion that we can arrive at, that will have strong implications for omega H1 and omega H2 that can get measured at high redshift using these measurements. So these are the things that I think the next stage that we can achieve with ongoing surveys like MALS, but obviously OH is a weaker transition, and in diffuse ISM, especially the cross section is smaller. So the major thrust may likely come from SK mid, where if we can target something like this, go down to sensitivities of 10 to 12 per centimeter square, the way we are doing it, able to do it for galactic studies, we can probably detect of the order of 100 OH absorbers with a survey which is similar in range compared to say MALS actually. So that is what I think maybe we can try to do over next several years on the way to understanding and making OH a very efficient tracer for H2, and all in radio where there is no dust bias. Yeah, thank you.
Thank you very much for that talk. It's good stuff.
Thanks.
Do we have any questions? Is he?
Yes. Thank you, Neeraj. And
Hi.
if you get back to the slide where you show the absorption of OH in four lines in the nearby galaxies. No, not nearby galaxies. Where you see the very high luminous OH absorption feature at 1720.
Yes, let me just share my screen again. I'm right now trying to search the Zoom window, which I have found. And I also found my slides at the same time. Yes. Yeah.
Yes, so
yes.
I think in the previous slide.
Yes.
Yes. So in the main lines, the second one, I think 67, there's
Yes.
two or three components on the left, and there's no thing detected in 16 in other main line. And
Yes. So third component is very weak. It's probably not required statistically in the case of 1665 megahertz.
oh yeah, I think I'm trying to understand this one. These guys.
Okay. This is the so this is the velocity plot centered at each of these lines. So this one is 1667, which is up there.
Oh, sorry.
Yeah. So
I
this is
misunderstood
velocity.
that.
Yeah. So this is x-axis is 0 kilometers per second. So each line is plotted in its rest frame, so that then we can compare in velocity space each one of the components directly.
Oh yeah. So I'm so sorry. I misunderstood that.
No worries. Actually, yeah, I should have explained what the x-axis is exactly. Yeah.
I'm wondering also with that bright emission that you have at 17 at the 1720 line. I'm wondering how much of that could be. Well, I mean, there could be a lot of masers in there as well, like bright masers that might be
Yes.
Yeah, that might not have much of a representation in the other lines. But then, of course, I would also expect to see that a bit in the main lines, but perhaps that's then overwhelmed by the absorption.
Yes, this is actually this is very true. In this case, the quasar sight line is passing through the center of the lensing galaxy. So and it's very high visual extinction also observed. And for this reason, this quasar does not have an optical spectrum at all, because it's like so highly extincted in optical and UV. And so this kind of activity is expected. There is another quasar at redshift 0.5 approximately, and that shows both H1 and OH. as well. And in that case, OH main lines and the satellite lines don't correspond to each other in velocity space. So they are like sort of disjointed. So it at least in this extragalactic system, there are some cases, I mean, very few detections to start with, but there are cases where we do see that satellite lines and main lines actually don't really necessarily correspond to each other.
Yeah, and I would actually expect that with extragalactic observations, because yeah, it's getting so much gas in there. Mm. Do we have other questions?
What's the velocity resolution in that plot, by the way?
Oh, so this is like about 6 kilometers per second.
Yeah, so quite a bit wider than you'd expect. You know, star forming maze.
And this is also integrated over like several kiloparsecs in the galaxy as well, right? Because the spatial resolution is like 10 arc seconds, and this is at redshift of 0.9. So we are seeing something which is integrated over. In case of absorption, it is integrated over the radio source practically, because in absorption we need a background illumination. But in case of emission, also it is like integrated over the entire beam. So that's another difference with respect to, say, galactic studies that happens here.
I guess it almost seems interesting in and of itself that we would still see the main lines in anything approaching what would be their ratio at LTE, because when you have observations that span such a large distance, it's not even the same gas necessarily, like you said.
Exactly.
Yeah.
So this is an exercise which I just did to see whether they're in LTE or not. But if they are not, I wouldn't mind. But if they are, I don't know what to do with it, because it is over. Because of the reasons that you explained.
Yeah. I think the main lines can look convincingly like LTE, but pretty much any time when we delve into a little bit more deeply that it's not actually. So there's not, like you said, there's not much we can do with that information.
Yes. But interesting thing is also, if I go back to say this particular system right here, here of course OH is very weak. We couldn't do VLBI spectroscopy with that, but with H1 we could do VLBI spectroscopy. And we find that the component which is corresponding to H1 is actually covers the radio source only partially, whereas this one covers the whole thing. So that's another. This is one of the measurement where I think we can indirectly say that like OH cloud is more compact than the cloud which is producing the H1 absorption.
Yeah, I think that's can you go down again? I think that's because of the line width of the main lines is so much wider than the 1712. So the line width of the main lines here, I think, what, about 200, 100 kilometers per second?
Yes.
So to me, it's like it includes mostly everything.
Yeah, this is
on our
the
lifestyle.
Yeah, this is the radio source, and this is the galaxy model practically. So this is like, because it's being lensed, it is actually offering much larger cross section to foreground galaxy.
Does anybody else have a question or a discussion point they'd like to bring up?
This is a great talk, and I'm too tired to come up with more interesting things to talk about. But other than the data is public, is that what you had said? Yes.
Yeah, for H1, all the data is public actually.
Okay, but for OH, it's not yet.
OH, we are still like looking at the data. We intend to make it public in a couple of months' time, actually. Maybe
Awesome.
next quarter, roughly. Yes.
Cool. And then, yeah, because something I've been interested in, but I have failed spectacularly at, was trying to stack extragalactic sources just using galactic H1 data and looking for redshifted OH, and that failed. So yeah, I was thinking maybe it might be interesting to try that just with like cross-matching a galaxy catalog and looking for redshifted OH, or just OH in general, just because you have the OH data.
Yes.
But yeah, not something I've really delved deep into, but I think your data set is definitely perfect for it.
Yeah, that's interesting. That's something which we are thinking if stacking can help, and we are trying to see if we can bin data meaningfully and then stack to see if a detection or detection can then help us understand something. It's just something we are right now working on. We don't have a result straight away on that, but I think we will
Right.
certainly have either a detection or non-detection, whatever that is, like in
Right. I think
near
at the
future.
least
Yeah.
you get non-detections. It'd be great if you get a detection, but I
Yeah.
also highly doubt it. But I mean, you can at
Yes.
least get an average stack of the H1 for like, some redshift
Yes.
range, and you say, okay, here's the average H1 profile, and then you look at the average OH profile. I suspect it won't be anything, but then you could say what the average OH to
Yes.
H1 ratio is in a particular
Yes.
redshift range, and like
Yes.
maybe that changes. I don't know.
Yes. I don't know. So for extragalactic redshift 0 to 0.1, we have a clean sample of about 30 absorbers
Okay, yeah.
of H1, and then of those 5 are detected in OH. But 3 are in 3 cases it is associated with the AGN itself. So it's like a
Okay.
different class of systems. But yeah, like remaining about 15, we can stack and try to see if they do show anything or not actually.
And then I was even trying just with Galpha H1, although I think I need alpha H1 from Arecibo because you have the redshifted OH in the H1 bands there. Just
Right.
cross-matching that with like a SDSS catalog and getting like 3,000 galaxies, and shift and aligning the the spectra or something, or however many galaxies you want in a redshift bin.
Yeah.
I did that and failed, so I didn't see anything. Yeah, I'm not sure if you would see like a global OH profile or anything.
No,
But
that
probably.
is understandable, because as I was saying that even when we take nice cases like this, in fact, even better than this, it's not that we do see detection in 100% of the cases. So when you take such sightlines and stack them, like maybe 70-80% of the time you are adding non-detections to it.
Non-detections, yeah.
And
Yeah,
that's why like your stacked signal is actually washed out.
Okay.
Stack signal is getting washed out because of the filling factor of the gas. I think it is not to do with the sensitivity. It is the filling factor of the gas which is killing the signal.
Yeah.
I don't know whether that is the way to look at it and interpret stacked measurement.
No, it's good to keep in mind. Yeah. Okay, so maybe just stacking where you would think you would get the OH absorbers is probably the way to go. Yeah. Yes,
that's why in this case of because we wanted to be reasonably efficient, because each sightline is taking 10 hours to observe. We did take only those in which 21 centimeter absorption we had already detected. Because there are other 70-80 non-detections which we did not observe because it makes no sense to them.
Yeah, because they're
But
not
if you can,
detections, yeah.
but you can imagine if we stack all of them, we wouldn't see anything, right?
Yeah, it's interesting. Okay.
Well, I would say if you do the stacking and then you add some weights on that, does that would it help?
Yes, I think we can add weights with respect to either strength or 21 centimeter absorption, for example, itself. Or H1 column density if we have. These would be the things to consider. And we are also considering to add weight with respect to visual extinction, so that like we can get some handle on the physical state of the gas. And latitude, of course, although our measurements are mostly high galactic latitude, but latitude also does, as we were having discussions related to scale height of gas and everything, like, so that can also be a very crude estimator of interpreting data. So these are the three or four parameters we are looking at right now. Yeah, maybe if we have a follow-up on 2 or 3 months, we will have something to show.
I mean, it's super exciting. It's really cool.
Yeah, something more messy than this.
I heard a saying once: more data, more problems. So we'll see what happens.
But speaking of that quote is a brilliant segue to what I was about to mention next, Michael.
Perfect.
About data sets. Because this kind of this survey and other things, it's really good for people to know what's out there and what's coming, and probably more importantly, where to find the data and who to talk to. So with that in mind, I've made another list. I've got a couple of shared documents now. I've put links to all of them on the homepage of the website. But let me just I haven't actually posted it in the chat. I put it in the chat as well. I've already put it in the Slack. But if we could also compile a list of any kind of data sets or surveys. Hey. Yeah, that's what it looks like.
Yeah.
So any data sets that you have or surveys that you know of that you're familiar enough with that you could facilitate somebody else potentially using them. Past, present, future, anything. It'd be great if we can compile that just to facilitate people being able to use these surveys a bit more.
That would be great.
And
sometimes we don't know from extragalactic to galactic and vice versa what data is actually already there.
yeah,
So.
of course. And there's I know when I was a student, there were so many times where, your supervisor or somebody might say, "Oh, just go have a look at X data." And you're like, okay. It's good to have a list. And also I would mention, because I'm about to add like some of my personal stuff on there, which is data that you get approved for proposals and you do the data, you take the data and then you never do anything with the data. That would be a great thing to add to that as well, because there might be somebody who that would be a nice supplement for their research. So yeah, anything and everything. We'll throw it in there. Do we have any more questions or discussion points while we have everyone still here?
I think we were also talking about surveys on Friday, right? So probably revisit.
Yes, we are. So that I was hoping in that one that we could talk about like upcoming, more future stuff too. But yeah, we are talking about that a bit more. And also potential future ones that we might want to start. Of course, if we already have a bunch of data kicking around, why in the world would we want to try and get more? But it's like we're like dragons with gold. We always need more data. All right, well, then thank you very much to our speakers, Michael, and to Neeraj. Thank you so much. And thank you to everybody who contributed to the discussion. And thank you to everybody else who attended. So it's so nice. Thank you. And we'll catch you in the next session, which is in what, an hour and a half or so? Okay, see you guys. Bye-bye.
Okay, so let's see.